Good day everyone. I am JB Ganesh. Today I will be presenting on error detection and correction. This topic underpins the reliability of digital systems we use every day for computers to communicate networks. I have discussing about error detection and correction. In this there are two examples like parity for detection and Hamming code for correction. These are used for errors. Let's start with the basics. Binary codes in digital systems, data is represented using only two digits 0 and 1. Each digit is called as a bit. This binary representation forms a foundation of all digital communication. It makes storing, transmitting, and processing information simply and efficient. Moreover, binary is easy to implement in electronic circuits and serves as a universal language for computers across the globe. Here the brief overview of today's talk. We will look at it, what binary codes are, why they are used. But binary codes uses only 0 and 1, and the various types of binary codes, how errors can affect data, methods used for detection and correcting this ethics errors, and we will see few practical examples along the way. Why binary codes? Binary codes are used for simply hardware circuit designs. These are important for the hardware circuit design and highly reliable are for digital systems. Binary data is also resistant to noise and errors, making it robust for the digital communication. This approach allows faster processing in computers and the reduced complexity means fewer errors and easier maintenance. Lastly, binary code is compatible with most modern memory and processor designs. And we have the dive into types of binary codes. There are four types of binary codes. Weighted codes, BCD, is an example, and non-weighted codes, gray code is an example, alphanumeric codes, ASCII is an example, error detection and correction. Parity is for detection and Hamming code is for correction. Binary codes are not all the same. They are weighted codes like BCD, but they are also non-weighted codes, gray. In this course, some error is detected, so we must detect and correct it. So by this, I have explaining that error detection and correction. It is complex. Introduction to error detection. Digital data is not immune to errors. Noise, interference, or hardware faults can corrupt data. During transmission or storage, ensures accuracy by spotting these issues. Many systems add schedule such as extra bits to detect or even correct mistakes. This process is crucial in minimum systems and communication systems, storage devices, and anywhere reliable data is needed. Ultimately, it prevents wrong decisions by missions that rely really on error-free computations. Next is error detection, and also called as parity bit. One of its simplest error detection methods is the parity bit, which adds a single bit to a string or a binary data. For every parity, the data number of ones in the data, including the parity bit, must be even. Here some examples. The simplest form of error detection is if for even parity, we must add ones for the number of ones must be to be even for even parity. If we add 1 to the parity bit, for the number of bits must be in odd number. It detects single bit errors widely used in memory systems. For example, if data, let us say 101001, for even parity, we add a 1 to make total number of ones even, resulting in 10100011. For odd parity, we add a 0 bit because it has a odd number of ones in it. If so, we do not want to add a bits to it. If flip the transmission, the parity check will be reveal an error such that tells us bit is wrong, only that something gone wrong. Like that, we have discussed that limitations of parity. Parity bits have their limitations. They only detect odd numbers errors. If two bits flip, the error goes unnoticed. This technique cannot pinpoint the faulty bit or fix it, and its effectiveness drops as data size increases. For future critical tasks, parity is not a reliable enough and more advanced approaches such as error correction codes are needed. Detects only odd number of errors. These simulations must be have misses even number of errors. It cannot have even number of errors, cannot correct data, only flags the data, not suitable for critical systems, need advanced codes for correction. Introduction to error correction. So how we can go behind simple error detection. Error correction codes are the answer. This allows systems not just to spot errors, but to actually repair corrupted bits in data. This capability is essential for applications that demand high reliability, such as satellite communication, deep space probes, and modern computers. Techniques include additional redundancy and algorithms capable of fixing common errors. This improves the data reliability and systems performance. By this, binary codes and error control methods like parity, this is the one of the topic that error correction. It is a crucial role. If we talk another that, now let us focus on one of the most widely used correction method, the Hamming code. It is a technique that invented by the Richard Hamming in 1950. His name is Hamming. So this method is called as Hamming code, and it was revolutionary because it allowed not just error detection but also error correction. Hamming code works by using multiple parity bits placed at specific positions in the data. These parity bits help in both detecting two-bit errors and correcting single-bit errors. These parity bits are placed at positions that are powers of 2, means 2 power 1, 2 power 2, 2 power 4, 2 power 2, 2 power 3, 2 power 4, means such as 1, 2, 4, 8, so on. This systematic arrangement makes it easy to calculate where the error has occurred. Today, Hamming codes are commonly used in RAM modules and computer networks, where data is integrated and extremely critical. So this technique is not just theoretical, but highly practical and widely implemented. This is the most widely used error correcting method because it has a high percentage of correction probability. This technique is all are using for the error correction in nowadays. Next is working of Hamming code. Now let us understand how Hamming code actually works. First, the parity bits are placed at position 1, 2, 4, 8, means the two powers, where 2 power 1, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, like so on. Each parity bit is responsible for the checking a certain group of data bits, and together they cover all the position. They cannot leave any position where empty in the code. It covers all position at the receiving end. The receiver compares the parity values. If all parity checks are correct, it means no error has occurred. It tells about if the checks the parity all are correct, it means no error has occurred. But if there is a mismatch, if we have a mistake, the position of the wrong bit can be calculated mathematically. By practically, it can be calculated mathematically. Once the bit is identified, the error can be corrected simply by flipping the bit. This restores the corrected. By flipping the bit, it can correct it. So in this, Hamming code ensures error-free data recovery with retransitions. That why it so efficient and powerful for communication and memory systems. Let us take an example that uh, let us now see a simple example of Hamming code in action. Suppose the original data is 1011 and encoded with parity bits. The transmission code becomes 10110011. Now assume that during transmission an error occurs and the received code is 1001011. The receiver then applies the parity check equations to locate the error. After calculations, the error is found to be position 3. Once the error bit is flipped, the data is successfully corrected back to its original form. This simple example clearly shows that how Hamming code is detect and corrects errors automatically, thereby ensuring the data remains reliable even in noisy environments. Conclusion: binary bits are base of digital code. It detects and corrects the errors where error detection and correction is the name for it. Prevents retransition and ensures reliable communication. The Hamming code stands out because of its simplicity and effectiveness, and still used in today in areas like computing memory, networks, and standard communications. And once more, parity is used for error detection, and Hamming code is used for error correction. Improves reliability and communications are essential in this. Thank you for everyone. This uh, seminar is about long length. Thank you for listening.